Hello everyone. In this video we look at one of the most successful models of the atom, which is Bohr's model of the atom, at least in the case of the hydrogen and hydrogen-like species. Now unlike the other scientists and Bohr's predecessors, Niels Bohr is actually theoretical scientist, while Rutherford, Thomson, they're all experimental scientists. The models that they have proposed for the atom are based upon the experimental observations that they have got based on either the discharge tube experiment in the case of J.J. Thomson or the alpha ray scattering experiment in the case of the Rutherford. But Niels Bohr came up with a set of assumptions which we also call as postulates, and the model of the atom is theoretical and is able to provide explanation to some of the the questions that were prevailing at that point of time, especially with regard to the spectral studies. Now when we talk about any successive model that comes, there are two important things that must be taken into consideration. One, the drawbacks of the previous model must be clearly answered, and second thing is any other prevailing questions must be explained by the new model of atom, or in general any model for that matter in chemistry. That is how we will look at the subsequent models, whether it is with regard to the models of the atom or even with regard to the models of chemical bonding. So when we go to the chemical bonding, we'll discuss about those things. But talking about the Bohr's model of the atom, there are certain important assumptions or postulates based on which the entire model is being developed. Now the main consideration of the Bohr's model of the atom is he is able to retain most of the things which were true, or rather which were holding good from the Rutherford's model of the atom. So Bohr's model considers that at the center of the atom there is a dense nucleus which contains most of the mass of the atom, which means there will be protons and neutrons inside the nucleus, and electrons will be revolving around the nucleus in circular orbits without emitting any energy. Now one of the drawback of the Rutherford's model is when we try to apply the laws of EM waves, the Maxwell's theory of electromagnetic waves, to the electron, then we see that electron must be emitting energy and should lose the velocity and spiral down into the nucleus. But what Bohr has proposed is this law of electromagnetic waves is applicable to all the fundamental particles or all the charged particles, but not to the subatomic particles, which means this law is not valid for the particles inside the atom. So this is one of the important assumptions of the Bohr's model. And the second assumption which is also there in the Rutherford's model is the force that is required to keep the electron in the circular path is being provided by the centripetal, is being provided by the electrostatic force of attraction between the nucleus and the electron. So every electron, since it is negative and nucleus being positive, the electron will be attracted towards the nucleus by the electrostatic force. So wherever the electron is present, we'll see that the force will be towards the center, and this force provides the necessary centripetal acceleration to keep the particle in the circular path. Now basically, in terms of the force balance, we will see that the centripetal force required to keep a particle in circular path will be mv square by r, which means this centripetal force must be equal to the electrostatic force acting on the electron. So this is the second important assumption of the Bohr's model. Now one of the most important assumptions of the Bohr's model is this Bohr's quantization principle, where as per this principle electrons cannot take each and every orbit. They will only be able to take those orbits where angular momentum is integral multiple of h by 2 pi. Now whenever a particle is in circular motion, let's say the mass of the particle is m, speed of the particle is v, and radius of the orbit is r, then the angular momentum will be given by mvr. So the angular momentum must be integer multiple. So n is an positive integer multiple of h by 2 pi. So the significance of this n is orbit number. Now the orbit which is closest to the nucleus will be given a value n is equal to 1, then comes n is equal to 2, then comes n is equal to 3, and so on. We'll see that at a later point of time this number will also be called as a principal quantum number, but for now we'll be using this n to represent the orbit number. So this equation is one of the most important assumptions of the Bohr's model, where Niels Bohr is able to quantize the possible orbits, and in this h is the Planck's constant. The value of h is as we know 6.626 into 10 power minus 34 joule into second. So this is the Bohr's quantization principle. Now with regard to the explanation of the spectral studies, Niels Bohr assumed that when the electron is revolving in an orbit, it will neither lose energy nor gain energy, and these orbits are basically called as stationary orbits. Now every stationary orbit will be associated with definite amount of energy, and we can also call these stationary orbits for that matter as energy levels. And later we will see that Niels Bohr is also able to derive the expression for the energy of the electron in these stationary states, and the outcome of that will be as the distance of the orbit from the nucleus increases, we will see that energy of that particular level will also be increasing, and these levels are either numbered 1, 2, 3, 4, 5 and so on, 1 being the closest to the nucleus, or they can be also denoted with these alphabets k, l, m, n. K will be the first orbit, l will be the second orbit, m will be the third orbit, n will be the fourth orbit, and so on. Now since we see that there are many such levels that the electron can actually take, most preferably we will be using the system based on the orbit numbers. Now when an electron is continuously moving in a particular orbit without losing energy, this level for that electron will be its normal state or the ground state, and when the electron is supplied with any energy, it will excite from that lower energy or the ground state to any of the higher energy levels. Let us say for example we take the lower energy to be the level 1, then it can go to level 2 or level 3 or level 4, and this process is called as excitation, and this particular state where the electron is getting into will be called as the excited state, and the energy amount that is absorbed will be exactly corresponding to the gap between the two levels. And since the electron cannot stay there forever in the excited state, which is high energy state, it will come back, and that process will be called as de-excitation, and during the de-excitation the same energy gap between the two levels will be released by the electron. So thereby as per the Bohr's assumptions, whenever an electron is absorbing energy or releasing energy, the energy that is being absorbed or released will be corresponding to the energy gap between the two levels. So if you look at the energy gap delta E between the two levels, that will be equal to the energy of the radiation h into nu. Now already we saw in the case of the Planck's quantum theory that the energy of radiation will be equal to h into nu or h into c by lambda. Now this is what is the Bohr's explanation for the spectral studies. Why only particular radiation are being present in the spectral studies? It is because of the idea that only the radiation which will correspond to energy gap between the levels in an atom will be either emitted or will be absorbed. So the radiation will be emitted during the emission spectrum, and the radiation will be absorbed during the absorption spectrum. Later we will see how based upon the theoretical derivations, Bohr's model is able to explain the spectral studies of hydrogen and hydrogen-like species. Now before we go into the derivations of radius, velocity and energy, which are probably one of the most important outcomes of the Bohr's model, since we are going to be dealing with charges here, we look at the basic aspect of force and energy that is associated with the charged particles. Now we learn in physics that two charged particles, let us say we are representing them with q1 and q2, will be able to attract each other if they are unlike charges, or they will be repelling each other if they are like charges. And the force magnitude, since force is a vector, will be given by k into modulus of q1 into modulus of q2 by r square. So here k is the Coulomb's constant, and the value of k in vacuum or free space will be 9 into 10 power 9 Newton meter square per Coulomb square. q1 and q2 are the respective charges, and r is the separation between the two charges. So the reason why we are using a modulus over here is to get the absolute value of the force. So this is what we call as the Coulomb's law of electrostatic force, and whenever there are 2 point charges separated by a distance r, this formula will give us what is the force between the two charged particles. And just like the gravitational force, electrostatic force is also what we call as conservative force. And for all conservative forces, we'll be defining potential energy. So if we have two charged particles q1 and q2 separated by distance r, then the potential energy of the two charge system will be equal to k q1 q2 by r. Now observe one thing here, that we are not using the modulus, which means if q1 and q2 are of different nature, then the potential energy will be negative, since one will be positive, other will be negative. If q1 and q2 are of the same nature, whether both are positive or both are negative, then the potential energy will be positive. And there is significance for this. A negative potential energy will basically indicate that it is a binding system, since two opposite charges, they will be always trying to bind to each other. And a positive potential energy will be indicating a repelling system, since like charges, if both are positive or both are negative, they will be trying to repel each other. So these are some of the basics about the charges and force and the potential energy of the charged particles. Now in the Bohr's model derivations, we are going to be using both these expressions, the energy expression for the two charges, potential energy, and also the force between the two charged particles, which is given by the Coulomb's law. So we'll go into the derivations of Bohr's model, starting with the radius. Now Bohr's model considered primarily single electron species, which means inside the nucleus there may be more number of protons, but there will be only one electron that is circulating around the nucleus, and the velocity of the electron, let us say, is v, and the radius of the orbit is r. Now the reason why Bohr's model is not valid for the multi-electron species is also because Bohr's model only considers the interaction between the electron and the nucleus. It does not take into account the interactions between one electron and the other electrons, which means this model will be valid only for the hydrogen and hydrogen-like species. Hydrogen-like species will be the species having single electron. Now we'll take a look at the derivation for the radius of the orbit. As per the electrostatic force law, if we look at the force acting on the electron, it will be equal to k into modulus of Ze into modulus of minus e. So here nucleus will be positive, Z times e, and electron will be negative, minus e divided by r square, which will be equal to k Z e square by r square. This is the force, and this must be equal to the centripetal force. Centripetal force formula will be mv square by r. So cancelling r here, what we will be having is mv square will be equal to kze square by r. Let us keep it as equation 1. Now we'll go into the other important equation that is given by the Bohr's model, which is equal to the angular momentum of electron is integer multiple of h by 2 pi. Now from the angular momentum equation, let us take the velocity value. Velocity will be equal to nh by 2 pi mr, and we'll substitute this in the equation 1. So what we are going to be getting essentially is m into n square h square. So in place of v square, I am going to use nh by 2 pi m r the whole square, n square h square by 4 pi square m square r square will be equal to kze square by r. Now 1 r and 1 r will be cancelled. On rearranging, we will be able to see that the value of radius will be coming as n square h square by 4 pi square m kze square. So this is the expression for the radius of the orbit as per the Bohr's model. Now to get this, we will take r to the right side and bring everything to the left side. So this is what is the expression for the radius of the orbit. And in this expression, as we can see, n is the orbit number which can change based upon the orbit. H is a Planck's constant, which will be always a constant. 4 pi square is a constant. M represents mass of electron. K is the Coulomb's constant. Z is a parameter which is the atomic number of the hydrogen or the hydrogen like species. And E is the basic charge, whose value will be 1.6 into 10 power minus 19 coulombs. On substituting the values of all the constants, we will get that the radius value will be 52.9 picometer into, there will be the parameter n square by z, or in terms of angstrom unit, it will be 0.529 angstroms into n square by z. So this is the formula for the radius of the orbits in both hydrogen as well as hydrogen like species. Now to derive the expression for the velocity, we are going to be using the value of radius that we got from the previous derivation. We know that velocity will be equal to nh by 2 pi mr. Basically, using the Bohr's angular momentum quantization principle. So mvr is equal to, so we are basically getting it from the mvr is equal to nh by 2 pi, Bohr's quantization principle. We want velocity means take m and r to the other side. So v will be equal to nh by 2 pi mr. Already we know the radius formula, which is n square h square by 4 pi square m kze square. On substituting it, we will have nh by 2 pi m. In place of r, we will be having n square h square by 4 pi square m kze square. So this will go to the numerator, which means nh into 4 pi square mk z square by 2 pi m into n square h square. Upon cancelling one nh, we can cancel m. We will be able to finally see that the expression for the velocity will be 2 pi k ze square by nh. Here other than z and n, everything else is a constant. So on substituting the values, we will get the velocity to be equal to 2.18 into 10 power 6 meter per second into z by n. So the parameter in case of the radius is n square by z, and the parameter in case of the velocity will be z by n. So this formula gives velocity of the electron in the orbits. Now depending upon the z value and the n value, the velocity of the electron will be changing. So this is about the expression for the velocity of the electron in the orbit. Now talking about the energy of the electron in an orbit, since electron is revolving around the nucleus, the electron will be having kinetic energy. So kinetic energy value will be equal to half mv square, and as we saw in the case of two charge system, so the nucleus is a positive charge and electron is a negative charge, potential energy will be equal to k as per the formula q1 q2 by r, so which is equal to minus kze square by r. So the total energy of the electron will be kinetic energy plus potential energy. Now when we look at the relation between kze square by r and mv square, already we have got the relation from the centripetal force balance equation. Centripetal force mv square by r is equal to kZe square by r square. This relation we got in the radius derivation. Centripetal force acting on the electron to keep it in the circular orbit will be provided by the electrostatic force on the electron. So on cancelling r, we will get mv square is equal to kZe square by r. So what we will be able to see here is the potential energy will be simply equal to minus mv square, which means we are able to see that the potential energy value is simply minus 2 times of kinetic energy. So thereby the total energy will be equal to kinetic energy plus potential energy. Potential energy is minus 2 times of kinetic energy, so it will be negative of kinetic energy. So the total energy value will be equal to simply minus half mv square. And already we have the expression for the velocity, which is 2 pi kZe square by nh. On substituting the value over here, we'll have the energy, total energy of the electron is equal to minus half m into 2 pi kZe square by nh the whole square. So this will give us the total energy expression to be minus 2 pi square m z square e power 4 k square by n square h square. So here you will see that the parameter will be z square by n square, and also one more significant thing is that the energy of the electron inside the atom will be negative. We are talking about the total energy. So upon substituting all the constant values, we will get that the energy of the electron inside the atom will be minus 21.8 into 10 power minus 19 joules z square by n square. Or in terms of one more common unit of energy with regard to these subatomic particles, where the energy will be less, is minus 13.6 electron volt into z square by n square. So this electron volt is a small unit of energy, and 1 electron volt basically is the energy required to move one electron through a potential difference of 1 volt. So 1 electron volt will be, the charge of electron is 1.6 in 10 power minus 19 coulombs, and you are moving it through a potential of 1 volt. So the energy required to do this will be 1.6 into 10 power minus 19 joules. This is the conversion between electron volt and then joules. So this is about the total energy of the electron inside the atom. So the value will be minus 13.6 electron volt into z square by n square. And as we can see, the energy of the electron depends upon both the orbit number as well as the atomic number of the hydrogen or the hydrogen like species. So this is about the energy of the electron inside the atom. And as we can see here, the significance of the negative energy is that the electron will be bound to the nucleus. Now based on the derivations of the energy for the stationary orbits, Bohr's model is able to provide explanation for the spectral studies, at least in the case of hydrogen and the hydrogen like species. Now as per the Bohr's model, if the electron is present in an orbit, say for example 1, the energy will be minus 13.6 electron volt into z square by n1 square. If say for example it is moved from the first orbit to, when I say first orbit, the orbit n1 to an orbit n2, the energy over there is given by E2 into z square by n2 square. So the energy gap delta E between the two levels will be E2 minus E1, which will be equal to minus 13.6 electron volt into z square by n2 square minus of minus 13.6 electron volt into z square by n1 square. So we'll see minus of minus will become plus, and we'll take the 13.6 electron volt into z square common out. The remaining entity will be 1 by n1 square minus 1 by n2 square. Now if this energy is emitted in the form of radiation, the energy of the radiation formula will be hc by lambda. So on rearranging, just bringing the h into c to the right side, we'll have 13.6 electron volt by hc into z square 1 by n1 square minus 1 by n2 square. Now if you closely observe this, this formula looks very much similar to the Rydberg's equation. So we know that the Rydberg's equation for hydrogen-like species will be 1 by lambda, which is equal to wave number r into z square 1 by n1 square minus 1 by n2 square. Now Bohr's model will be able to successfully explain the presence of characteristic radiation in the spectral studies if the value of this 13.6 electron volt by Hc is coming close to the Rydberg's constant, and that is what has exactly happened. If you look at the values of if you really substitute the values, 13.6 electron volt will be 1.6 into 10 power minus 19 joules divided by the value of H will be 6.626 into 10 power minus 34 joule into second, and C will be 3 into 10 power 8 meter per second. If we substitute the values, the value comes almost close to 1.09 into 10 power 7 meter inverse, which is the value of the Rydberg's constant. And this is the reason why Bohr's model is considered as very successful in explaining the spectral studies of hydrogen and hydrogen-like species, and that is what has actually increased the acceptance levels of the Bohr's model. So Bohr's theoretical derivations are able to completely match with the experimental observations that have been done on the spectral studies. Now we'll see that if you look at the energy of the electron in every orbit, the energy will be negative, and let's say for example we'll talk about the hydrogen atom first orbit. Now the energy of the electron in the first orbit of the hydrogen will be E1 is equal to minus 13.6 electron volt into Z will be 1 since it is hydrogen, and Z square by n square is the parameter. So first orbit means n is also equal to 1. The concept of ionization is if you have electron in any orbit, so here we are talking about the first orbit, we supply energy to the electron so that it will be removed from the atom. Now the theoretical way of looking at removing an electron from the atom is to excite it to n is equal to infinity. Now when you look at energy of any electron in the infinity orbit will be minus 13.6 into 1 square by infinity square, which will be 0. So the energy of the electron when it is in the infinity orbit, what we call as the ionized electron, will be 0. So if you want to increase the energy from minus 13.6 to 0, the energy that must be supplied is basically the finite energy level minus initial energy level, which will be simply equal to 13.6 electron volt. So we will see one relation here. When you are exciting, or rather when you are ionizing an electron from any particular ground state, then the ionization energy value will be simply negative of ground state energy. Since the ground state energy is always negative, we will see that the negative of negative will become positive. So the concept of ionization is basically to remove an electron from the atom, so which theoretically will be equivalent to exciting the electron to the infinity orbit. So this is what is the ionization energy. And we'll be able to see one more interesting relation between the energy levels. If you look at in a hydrogen, the first orbit energy will be minus 13.6 electron volt, and second orbit E2, this is the E1 value, E2 will be minus 13.6 electron volt into 1 square by 2 square, which will be minus 13.6 by 4, which will be nearly minus 3.4 electron volt, minus 3.4 electron volt. This is the E2. And if you go to E3, the value of E3 will be minus 13.6 electron volt into 1 square by 3 square, which will be minus 13.6 electron volt by 9, which will be minus 1.5 electron volt approximately. So the observation here is, if you see the gap between the first and second levels and the gap between the second and third, we'll see that the gap is going to keep on decreasing. And if you look at the energy of the fourth orbit, the gap between the fourth and third will be even lesser. So what we will be able to observe is the energy gap between the second and first will be more than energy gap between third and second, which will be more than energy gap between fourth and third, and so on. So this is one of the other interesting observations with regard to the energy levels in an atom. Now, while the Bohr's model is able to successfully explain the spectrum of hydrogen and hydrogen-like species, there are some drawbacks that the model had, and that is what has given rise to the subsequent models. One, in terms of the very basic applicability of the Bohr's model, it is only valid for hydrogen and hydrogen-like species, basically one electron species. The reason being the derivation itself, we have not considered the interactions between one electron and the other electrons. It is only assuming that there is a single electron present which is being influenced by the nucleus. And when the spectrum of hydrogen is studied with a fine spectrometer or high resolution spectrometer, as the technology keeps on improving, the same spectrum of hydrogen, when it is studied by using a powerful spectrometer, it is observed that what initially people thought as a single line is actually a collection of very closely packed lines. And while the Bohr's model is able to explain the original observations, this splitting of the spectral lines when seen by a high resolution spectrometer, Bohr's model is not able to provide explanation for this. And also one more interesting aspect is when the spectrum of any atom or element is studied by using an external magnetic field, there is a splitting of the lines, and that is what we call as Zeeman effect. And the same thing is observed even when an external electric field is applied, and that is called as Stark effect. So the splitting of spectral lines under the influence of magnetic field and electric field is one more area that Bohr's model could not provide explanation. And while Bohr's model is able to make a lot of theoretical assumptions, he was not able to justify the reason for these assumptions. While the Bohr's quantization principle MVR is equal to n into h by 2 pi is proposed as an assumption of the model, why the assumption is valid or the explanation for this is not being given in the Bohr's model. And while all of this is happening, one of the really important developments in chemistry is the discovery of the isotopes. So we'll see that even for some of what people thought really successful discoveries in chemistry, even the Mendeleev's periodic table, they have been completely decimated with the discovery of these isotopes. So as per the Bohr's model, since the energy only depends upon the atomic number, isotopes must be giving a similar kind of a spectrum. But it is found that the isotopes of hydrogen, so hydrogen has got 3 isotopes: protium H11, mass number 1 and atomic number 1; deuterium H21, mass number 2, atomic number 1. So we can also write deuterium as D21; and tritium H31, mass number 3, atomic number 1. So it can be written as T31. The spectrum of isotopes of hydrogen were not actually very much similar, but there were some differences, and this is one of the other things that the model is not able to explain. Now, a minor modification to the Bohr's model is what is being done by Sommerfield, who proposed the idea of multiple orbits in the same level. So while we think of a circular path which the electron can take at a particular energy level, as per the Sommerfield's theory, there could also be elliptical paths which will have slightly different energy in comparison to the circular path. So every energy level, what we thought as one major energy level given by the orbit number or the principal quantum number, is not just consisting of a circular path, but it could also be having one or more elliptical paths. And These elliptical paths are basically called as the subshells, and the subshells are being represented by one more quantum number called as azimuthal quantum number. So in a later lecture we'll see the details of what is the idea of the subshells and so on and so forth, but just to give an perspective on how the further models of atom were developed, we look at the Sommerfield theory. So Sommerfield theory gave an explanation as to why when the electron is jumping from one level to other level, there could be many spectral lines with a little bit difference in terms of the wavelength. It is because when we look at the energy gap between a circular path and elliptical orbit in the same energy level, they'll be very having they'll be having very minor difference in terms of the energy, and that is the reason why we'll be able to observe so many closed lines in the spectrum. So this is what is the Sommerfield's explanation for the splitting of the spectral lines when seen by the high resolution spectrometer. But then there are further observations of splitting of the lines in the presence of magnetic field and splitting of the lines in the presence of the electric field, and that is what is being observed in what we call as a modern structure of the atom, which is later modified into the quantum mechanical model of the atom. So in a later video we'll be able to take a look at it.